So let F be a field. Let F be a field. Then a non-zero polynomial, Px in Fx is said to be irreducible over F. You need to make sure of the fact over F. We'll see why. If first of all the degree is greater than or equal to 1 and there is no factorization, okay, there is no factorization of Px into Fx times Gx in Fx. So we are strictly inside the field with the degree of both of them being less than P, with the degree of G being less than the degree of P and degree of F also being less than the degree of P. Clear? Okay, fine. So we will make use of this a bit later, but for now let's keep it. Okay. The notion of irreducibility is actually a bit general. Okay, so we talk about the general notion first. A general notion of any over any integral domain or over any commutative ring with unity. Let us define that first. So basically, a non-zero element R in capital R, is said to be irreducible over R if firstly R is not a unit, and number two, if R can be written as S times T in R, then either S is a unit, or T is a unit. Yeah. Okay. Now observe the following. We know that all units over Rx are the units over R, are the units in R. Right? This is something we know. Okay. And this plays a very important role in case of judging irreducibles. For example, observe, and I had also said that you need to keep in mind that whenever we are talking about irreducibility of some polynomial over a field, we need to talk about irreducibility over that specific field or some other field, but we need to specify the field at any sense. Why is it so? Because observe that, suppose I talk about a polynomial in Zx. If in Zx, we consider the polynomial Px equals to 2x plus 2, then I can write it as 2 times x plus 2. Now observe that over Zx this is reducible. Reducible means not irreducible. Why? Because 2 is not a unit in Z, right? As it's not a, and therefore 2 is not a unit in Zx, and x plus 2 is obviously not a unit, is also not a unit. So I'm able to express the polynomial 2x plus 2 as the product of two non-unit elements over Zx. So therefore this polynomial is reducible over Zx, but if I analyze the same polynomial over Qz, over Qx, I can do this because Qx strictly contains Zx, right? Because Q strictly contains Z, right? Then observe that 2x plus 2 can be written as 2 times x plus 2, but 2 in Q over Q is a unit, right? Therefore, this polynomial is not reducible or rather irreducible over Q, right? So whenever we are talking about irreducibility of polynomials, we need to make sure over which ring we were talking about. Fine? Yeah. So this is a very good example to speak or let us start this lecture. Now let us talk about two aspects of the integers. Okay. Firstly, number one, we know that if P is a prime number such that P divides product of two elements, then this implies that P either divides A or P either divides B, right? This is your basic Euclid's lemma. Okay. But what if I convert this into ideal structure? We know that an element, so we said that an element is in an ideal if and only if P divides that element. Okay. What was the basic definition of division? So P divides an element, which means that A can be written as some x times P, where x is an element of that ring, right? So we can say that, so P divides AB is equivalently AB is in the ideal generated by P, right? So what I want is that this should imply that A is in the ideal generated by P or B is in the ideal generated by P, right? So this is one important aspect to observe. The second important aspect is that consider the group structure of Z and let P be the subgroup generated by P where P is a prime. Now then observe that then if K is some element in Z and the subgroup generated by K, it contains the subgroup generated by P, and obviously it should be inside the group of integers, then that should immediately imply that K divides P, right? Because if the group subgroup generated by P is contained in the subgroup generated by K, then that would imply P is in the subgroup generated by K, but that should imply P must be written as Nk for some n, right? But we know that K divides P implies that either K is 1 or K is P. But if K is 1, then the ideal generated by K is the collection of elements of the form n times 1 such that n is in Z, and that is equal to the whole group Z. Or if K is in P, then the ideal generated by K must be exactly equal to the ideal generated by P. So what do we conclude from here? That is, the group generated by P does not, or rather, there does not exist a proper subgroup of Z containing the subgroup generated by a prime element strictly. Okay, such subgroups are called maximal subgroups. Are called maximal subgroups. Okay. Okay. Now let us get into our discussion. Okay. So definition. Let a non-empty subset. Let us consider a non-empty subset of R, which is a strict subset of R. Then I, if in ideal of R, a strict ideal obviously, is called a prime ideal. So what we are going to do? We are going to imitate the property of a prime in the integers. So it's called a prime ideal if any product of two elements, if for all AB in R, their product is in I, should imply that one of them is in I, right? So this definition immediately implies the following fact, that the ideals generated by P in Z are prime ideals. Yeah, got it. Okay. And there is another important definition. Definition number 2 is that so we ordinarily define prime ideals by P. Okay. Now let phi not equal to M, or the more conventional notation is this, be a proper ideal of R, then M is called a maximal ideal. If M is called a maximal ideal, if there does not exist a proper ideal of R strictly containing M, strictly containing M. Got it? So also an immediate example of a maximal ideal would be an ideal generated by P in Z. This is again a maximal ideal. And in some sense, we are observing that since the same example works, intuitively we should think that whether prime ideals and maximal ideals have any correspondence between them or not. That is, can we say that every prime ideal is a maximal ideal, or every maximal ideal is a prime ideal, so on and so forth? Can we do such a discussion? Okay. So now that's not immediately true, but we'll come up with relative notions. Okay. So let's get into that. Now the first important property of a prime ideal is the following. Okay. You can take it to be a theorem will do. It's quite important. Okay. That is, let R be a ring. Let R be a ring. Then an ideal I in R is prime if and only if the quotient ring modulo I is an integral domain. Okay. So let's prove it, and the proof is quite simple. See, prove. Let R mod I be an integral domain. Okay. What does this imply? This implies that if A mod I and B mod I are in R mod I, then if their product is 0, but 0 in the ideal is basically 0 plus I, should imply that either A plus I is in I, sorry, A plus I is equals to 0 plus I, or B plus I equals to 0 plus I. But then this complete set of statements actually means that is if A plus B is in I, right, that is if AB is in I, this should imply A is in I or B is in I, which implies that I is a prime ideal, right? Because A plus I times B plus I is AB plus I, and AB plus I equal to I means AB is in I, but that should imply A is in I or B is in I, right? Conversely, let I be a prime ideal. Okay, let I be a prime ideal. Now, if 0 is equal to 0 or at the 0 bar, means I am talking about 0 inside the quotient range. So if 0 is equals to a plus I times b plus I, then that should imply ab plus I is equal to 0 plus I. That would imply ab is in I. But since I is a prime ideal, that should imply a is in I or b is in I. But that implies that either a plus I is equals to 0 or b plus I is equals to 0. What does that mean? That means that I, R mod I, is an integral domain. Obviously, start with the fact that a plus I and b plus I are non-zero elements. Non-zero elements in I. Getting my point? Okay, fine. So that's a good characterization of prime ideals, because from here something is very immediate. That is, if I take Z and if I choose P to be any ideal generated by a prime number, any ideal with P being prime, then what is the Z mod P? We know that this is isomorphic to ZP. But since P is a prime ideal, so this must be an integral domain. And that would immediately prove that ZP, Z modulo P or ZP is an integral domain. Right? We have proved this before explicitly as far as I remember, but this is an immediate proof as well. Got my point? Okay. Now let us observe the following. And this will again give us a large bunch of examples. Theorem. If F is a field and Px in Fx is a non-zero polynomial, then Px is irreducible if and only if the ideal generated by Px is a prime ideal. Clear? Okay. Now there is also an alternate definition of prime ideal which we did not require here, but in some books you will find we say that the ideal generated by some element is a prime ideal. It's a prime ideal, or sorry, we'll see this later. I'm not gonna use that notion immediately here. What we see is that if the ideal generated by some element P is a prime ideal, P can be any element. I'm not specifically talking about P being an integer. P can be any element, and we can talk about in any ring. If the ideal generated by some element is a prime ideal, then we say that P is a prime element. P is a prime element. Okay. Again, this is in 100% correspondence with whatever notion we have in integers, right? So what we are saying here is that, so initially what we had said that I is simply a prime ideal if the product of two elements is in I should imply one of them is in I, and one of the important motivations of it was the ideal generated by a prime number. Now what we say, so this is sort of a definition that an element is said to be a prime element if the ideal generated by that element is a prime ideal. Okay. So this theorem actually says that irreducible elements are in correspondence with prime elements. Yeah. Fine. Let's prove it. Prove. Suppose Px in Fx is reducible. Okay. Now let AB be in the ideal generated by P. But then that should imply P divides AB, right? But then since P is irreducible and P divides the product of two polynomials, then that should imply either P divides A or P divides B, right? By the Euclid's lemma for polynomials, this is something which you can immediately observe, right? But then what does this imply, right? This implies that either A is in the ideal generated by P or B is in the ideal generated by P. Fine. But we have not yet got with the fact that whether the ideal generated by P is a proper ideal or not. We need that for defining it to be a prime ideal, right? Okay. Now, wait a second. Is there some glitch? Okay, I guess there's some glitch. Okay, wait a second. Okay, right. But now, can we conclude that P is a proper ideal? See, P is obviously a proper ideal. P is a proper ideal. Otherwise, the ideal generated by P would be the whole of R, right? But once this happens, that would imply that there exists some polynomial f in Rx. Sorry, this should be Rx, such that fx times px is equals to 1, right? But this gives us a problem. Why? But this implies that now since obviously we are working in an integral domain, right? We started with f being a field, so we started with f being a field, but that would imply that the degree of f plus the degree of p must be 0. But that would imply that the degree of p must be 0, which is a contradiction, right? Because when we had defined irreducible polynomials, we had strictly said that the degree of that polynomial must be at least 1, right? Okay. Therefore, P indeed must be a proper ideal, and this implies that this ideal generated by P is a prime ideal. Okay. Conversely, what we can say? Suppose P is not irreducible. Suppose P is not irreducible. Irreducible, obviously, irreducible over F, since we are working strictly inside F. Okay. Then I can write P of X as Ax times Bx, such that the degree of A is less than P, the degree of B is also less than P. Right? Right? Okay. But observe that now every non-zero polynomial in the ideal generated by P is of degree greater than or equal to the degree of P, which implies that neither A can be in the ideal generated by P or B can be in the ideal generated by P, right? Because they are having degrees strictly less than P, and for them to be inside the ideal generated by P, their degrees must be at least degree of P. That is not possible, right? So what does this conclude? This concludes that the ideal generated by P is not a prime ideal. Therefore, by choosing contrapositivity, we are done, right? So what we immediately conclude from here is that if you are in some uh, polynomial ring over a field, if you're in some polynomial ring over a field and you choose any polynomial which is irreducible over f, then that should immediately imply that fx mod px is an integral domain, right? Okay, see some useful examples. What can you say about Rx modulo x? See, this is actually isomorphic to R, right? Why? Because what we can do is that we can choose a map from Rx to R, take some polynomial here, map it to f of 0, right? This will give us this ideal as the kernel, and we can also observe that this ideal, or rather this polynomial x, is irreducible over R, right? So that should imply that R is an integral domain, right? Which is already quite obvious previously, but this gave us also an immediate proof from this fact, right? Therefore, the ideals, or rather an element is irreducible if and only if it is prime. So what do we conclude from here is that, so over fields or polynomial rings over a field, a polynomial is irreducible if and only if it is a prime element. Clear? Okay. Now what we want to do, so we had also defined another sort of an important ideal called the maximal ideal, and what we want to do is that we want to characterize that. So what we can do is that a proper ideal I in R is maximal if and only if the quotient ring mod I is a field. Okay. Okay. Now see, here also the proof is quite simple. Proof. See, we know by the correspondence theorem, all the ideals in R mod I are of the form, quick recall, are of the form J mod I, such that I is contained in J and J is an ideal of R, right? But now, if R mod I is a field, then the only ideals in R mod I, by the definition of field in R mod I, are which one? Either it's simply R mod I or it's 0 mod I, which is exactly equal to I itself, right? So what does this mean? This means that the only ideals in R containing I are either I itself or the whole ring R. So that implies that I is maximum, right? Because one of the ideals should be R and the other ideal should be 0, but I mean 0 mod I in terms of that, but 0 mod I is equivalent to basically speaking about I. Because what is the 0 element in the quotient ring? It's I itself, right? It's just I, right? In that sense I'm talking. Got my point? So the only ideals in R by the correspondence theorem should either be I or R. That should immediately imply that I is a maximal ideal. And the converse is also the same, right? The converse holds in the same way. Right? That is the complete set of statements is actually an if and only if statement immediately. Because if I is a maximal ideal, then the only ideals containing I and R, I is either I itself or R. But then correspondingly, the only ideals in R mod I should be 0 mod I or R mod I, right? And hence, what do we conclude? That so therefore the only ideals must be either the 0 ideal modulo I or the whole ring R modulo I, and therefore R mod I must be a field. Clear? Now this immediately proves a very important thing. That is lemma, or actually this is a rather a corollary, that in a ring maximal ideals are prime ideals. Are prime ideals. Why is it so? The proof is very simple. Let M be a maximal ideal in R, but that implies that R mod M is a field, but we know that all fields are integral domains. So that means R mod M is an integral domain, but that means that by the categorization of prime ideals, M is the prime ideal. Fine. Now the question is the converse true? Obvious question, right? Is the converse true? Okay. So to check the converse, now see, whenever you talk about a converse of something, I would always say do not immediately jump into conclusions that whether it's true or not. Whenever you want to judge something as a converse of some theorem, the first thing which you should be taking care of is whether there is some examples or not. You should always talk via examples. Okay. Otherwise, you some sort of can feel that the converse, yeah, the converse feels to be so obvious and so it should be true. But now observe the following example. Wait a minute. Yeah. Example. Consider zx mod x. Then we know that it is again isomorphic to z by the same map, base same evaluation map. Choose phi from zx to x, map a polynomial px to p at 0. Right? But z is an integral domain, not a field, which is not a field, which is not a field. But that implies that the ideal generated by x is a principal ideal, since z is an integral domain, but not a maximal ideal, since z is not a field. Okay, but not a maximal ideal, right? But if you recall, in the integers, we had seen this, that when you talk about an ideal generated by a prime number, then that was equivalently a prime ideal as well as a maximal ideal, right? Okay. Wait a second, wait a bit. So now the next important theorem in this part is the following theorem. Now this is very important. Observe, if R is a PID, that is, it's a principal ideal domain, then every non-zero prime ideal, or rather prime ideal, is a maximal ideal. Okay. And observe that we had proved it previously that Zx is not a principal ideal domain, because we had proved that the ideal generated by 2 and x, this was not a principal ideal, but it is obviously an ideal of Zx, right? Got my point? Therefore, the correspondence between maximal ideals and prime ideals, non-zero prime ideals, holds whenever we are talking about principal ideal domains. And the proof is again quite simple. See, so what we want to prove? We want to prove that every non-zero prime ideal is a maximal ideal. So p, let 0 not equal to p in R be a prime ideal. We need to show that it's a maximal ideal. Okay. So let j not equal to I be an ideal of R. Okay. Now to prove that I is a maximal ideal, what do we need to show? So therefore, we require to show that j must be equals to R, right? Because I have already assumed that j is not equal to I, and for I to be a maximal ideal, there cannot exist a proper ideal which contains I strictly. Therefore, j must be equals to R. Right? Now, since R is a PID, I know that this prime ideal is generated by some element A, and this ideal j is generated by some element B. Right? Right? Now, observe the following. A is in J, right? Since I is in J, right? What does this imply? So this implies that I can write A as some R times B, got it? Where R is in R and B is in J, because J is immediately generated by B itself, right? But I is a prime ideal. Sorry, I chose P, right? Sorry. But see, P is a prime ideal. And A is in P because A generates P. So that implies R times B must be in P, right? But if R times B is in P, what does this imply? This implies that either R is in P or B is in P. Right? Now, if B is in P, then that would imply the ideal generated by B is contained in the prime ideal P, but that would imply J is in P, which is a contradiction, because we had assumed that J strictly contains I, right? So that implies R must be in P, right? But that implies I can write R as S times A for some S in R. Right? Therefore, A, which was R times B, this is actually S times A times B, right? That implies A times 1 minus SB is equals to 1. Since A is non-zero, because we were talking about a non-zero prime ideal, so the generator cannot be 0. This implies 1 minus SB, so this is 0, so 1 minus SB must be 0, since R is an integral domain, right? But that implies B is a unit. Once B is a unit, that would imply the ideal generated by B, which is exactly equal to J, must be the whole of. Got it? Okay, fine. Yeah. Okay. Let's continue. Okay, have I screen shared? Right. Fine. So now what we have proved is the following. Okay. So what we have proved is the following, that now if F is a field, then we have seen previously that Fx is a principal ideal domain. Recall how we had proved this? If I is some ideal in f of x, then choose a polynomial px in I such that the degree of p is the least positive degree in I. We have done this. Then we have proved that I is generated by this polynomial itself by just simply applying the division algorithm, right? So what we have proved is the following, that therefore all irreducible polynomials in fx generate a maximal ideal, right? Because what we have proved is that we had proved previously that irreducible polynomials are prime elements, that is, they generate a prime ideal. And what we have shown that in a PID, every non-zero prime ideal is a maximal ideal. Once we talk about irreducible elements, we are strictly talking about non-zero elements, so the ideal generated will be a non-zero ideal. Since it's irreducible, the element must be prime, so the ideal generated must be a non-zero prime ideal. Hence must be a maximal ideal since fx is a PID, and hence all irreducible polynomials generate a maximal ideal. What does this conclude? So this concludes that all quotient rings modulo ideals generated by irreducible polynomials are fields. And that immediately proves a very important statement as the existence of a finite field, which we had seen previously though, of a finite field. That is the following, that if I choose the ring of integer z, and so we know that z is a principal ideal domain, right? And let's say p is a prime ideal, is a non-zero prime ideal, that is p is a non-zero prime number. Then z mod p, which is isomorphic to zp, is a field, and zp has only p elements, right? So a non-zero prime ideal should be a maximal ideal. That is what we are making use of. Okay, right. And in fact, this is the introduction in any case of field extensions. Because now observe the following: if I choose the rings over the field Q, and I choose the polynomial x square minus 2 in Q, then we know that this is irreducible over Q. We haven't proved it, but I guess we had discussed this previous, that polynomials of degree 2 or 3, polynomials of degree 2 or 3 are irreducible, if and only if there does not exist a root over the field, right? And the root of this should be plus or minus root 2, that is obviously not a rational number, so it does not have a root over Q, and hence it's a reducible element. This implies that the quotient ring Qx modulo the ideal generated by x square minus 2, this must be a field. And over field theory, this is what we express as Q root 2, that is the smallest field. So this is the smallest field containing Q and the element 2. Clear? Got it. Fine. In a similar way, observe that let us talk about Rx, and let us choose this polynomial Px in Rx such that P of x is x square plus 1. Then this is irreducible over R, and therefore Rx modulo x square plus 1 should be a field, right? But in this quotient ring, if you recall how we had talked about the elements inside the quotient ring, in this quotient ring, every element corresponds to the property that x square is equals to minus 1, right? Because if I choose any element from here, it must collapse in this way, right? Because x square plus 1 must be 0 in Rx mod x square plus 1, right? So that implies that x square must be equals to minus 1 in Rx modulo x square plus 1. And this element x is what we identify as iota. So basically this field is actually your complex numbers, which you also denote as Ri. That is the smallest subfield, or rather the smallest field containing R and the square root of minus 1 by a slight abuse of notation. Got it? Is it clear? So this is some sort of a construction of the complex numbers through algebra. Yeah? Okay, fine. Because see, now you can obviously say that such an x might not exist over this quotient ring, right? You can obviously have that notion. But how are we constructing this quotient field? This quotient field is being constructed in a way that in some sense we are adjoining the root of this polynomial here, right? See, let me be a bit precise in order to give you a subtle construction of complex numbers. Okay, observe that. So this is a way in which we talk about field extensions. Let k be, yeah, we can do it in this way. Okay, fine. Let us do it in this way. Think. Okay. Consider. I'm not actually getting a what I want to do. Let me think of something. Okay. Consider some element alpha in K which contains F. So the K is a field, F is a subfield of K. Okay. Consider the map phi alpha from Fx to K by what we do. So we map a polynomial to its evaluation under alpha, right? Yeah. But then therefore by the first isomorphism theorem, what should we get? That is phi alpha of fx divided by the kernel of phi alpha. This should be isomorphic to f alpha. That is polynomials, or rather, sorry, not this. Okay, right? It should be isomorphic to f alpha. That is polynomials evaluated at alpha. And you can observe that this is actually a surjective homomorphism, right? Fx to f alpha via this map is a surjective homomorphism. Surjective, yeah. Getting my point? Now, if fx is a PID, which is we are sure about this because f is a field, then there must exist some monic irreducible polynomial px in fx such that the kernel of phi alpha is generated by this element p, right? Getting my point? So what do we conclude? So we conclude that ft by pt should be isomorphic to f alpha, right? Getting my point? But since p is irreducible, this must be a field, so it also satisfies the condition that, so yeah, so yeah, what we are saying that so p is irreducible and it's a PID, right? So since p is irreducible, so this must be a field, right? Ft mod pt must be a field, so this must be a field asset. Getting my point? Okay, fine. So what does this actually give us? So this in fact gives us the following fact, that this will actually be a field. Okay, and this is what we actually say to be f alpha, that is the smallest field containing f and alpha. Now, so how does this relate to our? Suppose I is an element which satisfies, or which is a root to x square equal to minus 1, right, over R. Getting my point? Therefore what we can do, therefore I can talk about Rx mod x square plus 1. This would give me R at, so I would want to evaluate it at the root, right? I would want to evaluate it at the root at which this becomes 0. So I would immediately want it to be, because observe that when we generate the kernel by this element p, then p of alpha must be 0, right? And since it's a monic irreducible polynomial, therefore every other polynomial such that it, alpha is a root of that polynomial would imply that p must divide that polynomial, Right? So it is basically R evaluated at I by this ordinary element I. Right? And this is what your C is. Getting a point? Right? And if you don't want to get in such sort of complications, you can think it to be simply in this way, that since we have already proved that this is a field, right? And any element of the form a plus x square plus 1, or rather inside here, if I talk about the element x or rather x plus x square plus 1, let's say. Okay. So this is an element in Rx, modulo x square plus 1. Then if I square it, I should get this. But this is minus 1 plus x square plus 1, right? So these elements, or rather x corresponds to the element minus 1, right? Or rather, x can be identified by I. Got my point? Right. It might sound a bit confusing, but I would ask you to just go through this part in very details, and you will get to know what I'm trying to say. Okay, fine. Yeah. So yeah, we have discussed a lot about these things precisely. Now let us do one last theorem, and we will end this part here. Theorem: if R is a PID, sorry, I have already discussed this. If F is a field and Px is in Fx is irreducible, then the quotient ring Fx mod Px is a field. This part we have already proved that it's a field containing an isomorphic copy of F and a root of Px. And this is exactly the thing which we had discussed previously, right? This is exactly the thing which we had discussed previously. So let us give a formal proof of it. Proof. We already know that Fx modulo Px is a field, right? Because F is a field, so Fx must be a PID, and Px is a irreducible element, so it's a prime element. It's a non-zero prime, so it will generate a non-zero prime ideal. Hence, it will become a maximal ideal, right? Now, map A to A plus I from F to let's say F prime, which is A plus I, such that A is in F. Got it? Yeah. And so this should be contained in Fx modulo Px. I is your Px. This is your Px. Okay. Fine. Because all the constant polynomials are basically elements of that. So this will give an isomorphism. Right. Therefore, F is embedded inside this field. Right. Therefore, F is embedded inside this field. Now, whatever we are going to do is the very basic introduction to field theory, and you can in fact consider this to be a very important proposition in field theory. That is, so what do we actually conclude from here? What we'll say it later, but let me just start it down. That for a field F and an irreducible polynomial P over F, there exists a field containing F. That is, there exists a field extension containing F and a root of P. So what do we typically conclude is that every irreducible polynomial over some field has a root in some field extension. You can always get hold of a field extension which will contain some root of an irreducible polynomial of the smaller field. Got it? And therefore, this actually also concludes whatever I was trying to discuss. That might have felt a bit confusing, but I guess you people will now have an idea that x square plus 1 was irreducible over Rx. So we will get hold of a field extension where x square plus 1 admits a root. That is exactly what we denote as I, and this will give you the imaginary number iota, and C is basically exactly this quotient ring, right? Okay. So let's get back to the proof. Okay. Now since okay, or rather let theta b is equals to x plus I. Okay, and we had in fact proved the same thing when we had proved about the existence of iota, that x plus I actually corresponded to the element root over of minus 1, right, in Rx modulo x square plus 1, right? And we'll choose the same element. That does the job. Let theta b is equals to x plus I. We claim that theta is a root of Px. Please go through this very carefully. You will get to know what I'm trying to do. Now let Px be written as a0 plus a1x and so on till an x to the power. Now see, we could have also chosen a monic polynomial. Why? Because we are working inside a field. An is assumed to be non-zero, so I can define the whole polynomial by an, and I would have chosen the new polynomial to be the monic polynomial. But I think it won't make any difference. So what is p of theta? So this should be a0 plus I, or rather let me first place it inside and I will talk about it obviously. So it is a0 plus a1 times x plus I, so on and so forth, till an plus I. Oh no, I'm doing a bit of mistake. I'm doing a bit of mistake. Sorry. Then px plus I is so I'm taking this polynomial inside the quotient ring. So this is of the form a0 plus I plus uh, a1 plus I into x plus I, so on and so forth, till an plus I into x plus I to the power n. So this is basically a0 plus I plus a1 plus I into theta, so on and so forth, till n plus I into theta to the power n. Right? Right? Okay. Hmm. I shouldn't have written this immediately. Let me erase this step a bit. Whenever I'm see, since if I would have done this, just in my pen and paper, I wouldn't be so confused. But when I'm lecturing on this, I need to be exactly accurate, and so there often arises some sort of confusion. Okay, please pardon me. So then, over uh, fx modulo px, we can write p theta as, yeah, now I am structuring it correctly. See, whatever I was doing, that was correct, but that was not well structured. To give a proof, I need to be well structured. Okay, that was sort of a scratch word for a proof. So this becomes a0 plus I plus a1 plus I into theta, so on and so forth, till an plus I times theta to the power n. That is equal to a0 plus I plus a1 plus I into x. So this should be x plus I, right? So on and so forth, till n plus I into x plus I to the power n, right? But that is exactly equal to x to the power n plus I, right? So now this can be written as a0 plus a1x and so on till an x to the power n plus I. So that is equals to px plus I. But what was I? I was this itself. This is something which we have chosen to be I. So this is 0 in uh, fx, because 0, or rather 0 bar, right, in px. That is basically that is basically good one. Right. So what do we conclude from here is that therefore p of theta is 0 in the quotient ring, quotient field rather. This implies that theta is a root of p in in fx modulo p, and therefore p admits a root, right? Okay. So as I was saying previously, that if you consider Rx mod x square plus 1, then that R is embedded here, and this is basically isomorphic to what we call the complex field, and here eta is responded with x plus 1. Got my point? Okay. Fine. Yeah. Let me give some two or more topics as well. Let me just stop here. Okay. Definition: a polynomial f of x in fx, it splits over f if it is a product of linear factors in f. That is, all the roots of p are in f. Okay. Example: x square plus x square minus 1 in Rx. Then I can write x square minus 1 as x minus 1 into x plus 1. So it's a product of linear factors in R. So this splits over R. But x square plus 1 in Rx does not split over R. Split over R. Yeah. For example, x cube minus 1 is a polynomial in Rx. But I know that x cube minus 1 is x minus 1 times x square plus x plus 1. And so it does not split over R. Does not split over R. Because the roots of this should be omega and omega square, the cube roots of unity, the non-trivial cube roots of unity. And these are not real numbers, so they are not in R. Right? Okay. Now we prove another very important aspect of field theory, theorem. And this theorem is due to Kronecker, who said the following, that let fx be a polynomial over a field. So it's a field, f is a field. Then there exists a field E containing f over which fx is a product of linear factors. That is, Fx is the product of linear factors, that is Fx splits over E, that is E contains all the roots, of, clear? Okay. And the proof is actually pretty simple. Proof, we induct on the degree of f. Okay. Now if degree of f is 1, then f is linear, so it's already linear, right? Then f splits over f itself, so I can choose E to be just x. Okay. Otherwise, if the degree is greater than 1, let f of x be written as gx into px, where p is irreducible over f. Then we know from the previous theorem there exists a field B containing f and a root of px, say theta. So px can be written as x minus theta times some polynomial hx in bx. But then if I simply induct on the degree, then what I can say is that, but then by induction there exists a field E containing B such that hx, see what is the degree of px, right? Such that what I mean to say is that the hx splits. Hence, hx splits. Got it? Yeah. Okay. So I think my audio source has very low charge, so I'll need to stop this lecture here. In the next lecture, we will give a very important example of the Kronecker theorem, and we will dive into some deeper topics. For example, our next target would be the notions of repeated roots. Okay. So meet you guys in the next lecture.